I thought it was a woodman.
All right, here we go. Referencing the pre-quiz. MGH. Gentlemen. MGH. So potential energy is the potential for the conservative force, specifically gravity, to do work. Okay? So if you had a box at an elevated location, does gravity have the potential to do work? How much work? Well, if we dropped it, that'd be force parallel times distance. In this case, the force doing work would be the force of gravity, and the distance that it would fall would be equal to the height. So the work, now we know that force of gravity is equal to mass times 9.8. So mg, force of gravity, times h. Hey, look at that. Boom. So potential energy is the potential for gravity to do work. Okay. Do that. Yeah. So okay, stab at that one. Tell you the answer to that one. Correct answer is D, dangerous dinosaurs, any of these. Depends on what you define as ground zero. So, if you made the tabletop, we'll just say this, look at the stapler. If we made the tabletop ground zero, then the height would be 0, and it would not have potential energy.
And potential energy is also equal to kinetic energy.
Sometimes. So if we drop this, it hits the ground, we're like, oh, maybe we should make the floor ground zero. That's so now it does have potential energy. We'll say 20 joules. And then we realize, what would happen if they had an earthquake? And like, we're on the second story, and like the building split open.
This isn't 2012. We're not watching Los Angeles sink into the ocean.
Okay, but if we were,
Nor are we getting
we would make ground zero the dirt outside. Good with that? So all of these are accurate, valid. It just depends on what you make ground zero. So how do you know what you make ground zero? The answer to that is the lowest point you care about, make that ground zero. If the stapler never falls off the table in the situation that you're trying to evaluate, make tabletop ground zero. If it does fall off to the floor, well, then make the floor ground zero. If, the end happens, it gets split open. But if it never does that, don't worry about it. Okay? Good with that? All right. So you might want to reference the notes you took during the pre-quiz. Thumbs up when you have a guess. Tell your neighbor why or why not.
There's more. Yes. My guess
Okay. Your ability to answer this question, it was 100% dependent upon if you did the pre-quiz or not, or you watched the video. Okay, so forces acting on it: gravity, normal force. Okay, mechanical energy is conserved if there are no non-conservative forces doing work. Okay, gravity, is that a conservative or non-conservative force? It's a conservative force. In this class, it's the only one that we're going to worry about. So we're good with gravity. Normal force, is that a conservative or non-conservative force? Non-conservative force. Okay, like, oh, highly suspect. But the condition isn't, is it acting, but if it's doing work. Is normal force doing work?
No.
Why not?
Because it's perpendicular to.
Right, there's no component of that that's going parallel to the direction of motion, is acting perpendicular to the way it's moving. No work is being done by the normal force, so is mechanical energy conserved? Yes. Mechanical energy is conserved. Good with that? Try this one. Thumbs up when you have a guess. Have a conversation.
I was afraid because there's unconservative force doing work, which would be pushing on the car.
Alright, what do you say? Thumbs up for yes, it's conserved. Thumbs down for no, it's not conserved. What do you say?
What? What?
Okay, good. So, gravity, conservative force, normal force, non-conservative force doing no work, applied force, conservative or non-conservative force? Non-conservative force. Is it doing work? Yes. It is acting. There's some component of that that is parallel to the direction of motion. All of it is parallel. It's just in the acting in the opposite direction of motion. Okay? So, but then you're asking, like, what? It's going at a constant velocity. Does that count for something? I mean, it does, but not for mechanical energy. What you know is the sum of the forces are equal to 0. Okay? Therefore, you know that the net work is equal to 0. And the change in kinetic energy is going to be 0. It's not going to change because it's moving at a constant velocity. That's all well, true, and valid, but that does not speak to mechanical energy. Mechanical energy would not be conserved.
Um,
Okay? Spencer.
Also, note that there's also a hint The literal guy is saying the answer.
Yeah, there it is.
Like, no.
All right.
Going over by 1
So, mechanical energy, the change in anything. So, if something is conserved, there is no change. But if it's not conserved, then there is a change. All right, with that idea? Okay. So the change in anything is final minus initial. Okay. Now, I've found that the negative sign kind of messes with people. So I'm gonna bring this over here. Okay. So I'm gonna say initial mechanical plus the change in mechanical energy is equal to your final mechanical energy. Remember that?
Yes.
Good. Okay. Now, we know that the work done by a non-conservative force is equal to change in mechanical energy. Correct? Free quiz? Okay. So, these two are interchangeable. Okay with that? Now, we also know from the pre-quiz that mechanical energy is equal to the sum of kinetic energy plus potential energy. So what I can do here is write initial kinetic plus initial potential plus the work done by a non-conservative force is equal to final kinetic plus final potential. That last line, that's going to be your original equation for a lot of these problems. Okay? That's going to be your happy place, right here. Okay? Good with that? Okay. I recognize this is archaic, but there's a lot of information here. A lot of stuff you can glean. Okay?
So it's not packed ice, it's just ice. You're stuck.
So on the hill, I'm going to say frictionless. Is mechanical energy conserved as it goes down this icy embankment? There's no non-conservative forces doing work. And so what you see here is this. At the height, at the beginning, it's all potential energy because it has height. As he decreases height, the total mechanical energy stays the same. Where does that go? Well, that goes to kinetic energy as he gets faster. Bless you. Does that make sense? Okay. Now, at the bottom, you've got gravity, normal force, and friction. Is friction doing positive or negative work? Negative work. Okay, is that a conservative or non-conservative force? Non-conservative force. So as he goes, distance is covered, more work is done in the negative, and we're causing total mechanical energy to be lost. You okay with that? As I pass out some pennies, marinate. Ooh, in this animation.
Should we do it opposite use.
I see one with the
Yeah, I'll see the scrap, but I was It's easy. It's like two proper knife. It's been a second since I've done that. Was the chapter last year that was 1083? Was this it? These three circles? Because I knew most of it, but like, there's some parts From tribe. I'm just trying to think of this. Again. Yeah, but he was the first one that emailed. He like emailed. Yeah, no, it's because. Just stop by and stop by and
Here we go. So, this is a really simple example. Okay, but I want you to like get it. So initially, you have 100 joules of potential energy at the highest point. Kinetic energy is 0 because it's at rest. Mechanical energy is 100. As it goes down, we have 75 joules of potential energy, 25 joules of kinetic energy. Total mechanical energy is still 100. It's conserved. Okay. So how much kinetic energy would you have at this location? 50. How much potential energy would you have at this location? And here you'd have how much potential energy? 0 and 100. It's just that easy. Okay, good with that? All right, so my analogy is we're going to compare energy to money. Okay, you're going to have, so on your notebook, draw like an inch by inch square, 2 of them. Label one savings account, and the other checking account. Big enough that a penny can fit in there. Doesn't have to be crazy. This is just
Make sure the square is like
doesn't matter.
the diameter of a penny.
Okay. Good with that. Savings and checking. We're going to say our savings account is potential energy, and our checking account is kinetic energy. Mechanical energy is how much energy you have total in the bank. Okay? Checking plus your savings. Okay? Work done by non-conservative force, that's going to be either depositing or withdrawing money out of the bank. Okay? If you're depositing, that's a positive work. If you are withdrawing money, that's negative work. Good? Okay, so here we go. Step 1 is we need to define where our initial and our final locations are. Initial, highest point, final, wherever they stop. Okay? Step 2, we need to define where ground zero is. The lowest point we care about is where we need to make ground zero. Like this height here, that's ground zero. Okay? Not too brain busting there. Now, initially, do you have kinetic energy? How do you know? Kinetic energy is equal to 1/2 mass times speed squared. Right, Micah? Yeah, didn't even catch that one. Is it moving? That is what we're asking ourselves. Okay. Is it moving? Okay, so at the initial location, does it have kinetic energy? It does. It's moving, right? The kid's moving. Okay, so I need to give it some kinetic energy. I need to put some money in the checking account. How much? It really doesn't matter. I'm going to throw in there 5. 1, 2, 3, 4, 5, just for kicks and giggles. Okay. At the initial location, does it have gravitational potential energy? I don't know. The question we're asking ourselves is it above ground zero? At the initial location, is it above ground zero? No. Okay, so our potential energy is nothing. So the first relationship is we're asking ourselves how much money is in the bank. Okay, so we've got checking plus savings gives us total. So we got 5 pennies in the bank. Good with that? That's relationship number 1. I don't really care how many pennies I had here and here, but I do care about that this relationship is consistent. So your kinetic plus your potential gives you your mechanical. Good with that? Okay. Relationship 1. Relationship 2. We're now looking at the process from the initial to the final, and we're asking ourselves, is there any work done by a non-conservative force?
You gave me 13.
That's a problem. You're welcome. You are welcome. So, in this process, was there any work done by non-conservative force? No. We had friction and normal force. No friction. Just kidding. Normal force and gravity. No work being done. So, we can say there was no spending or earning. There's no withdrawal or deposit. So, how much money do we still have in the bank? We still have 5 pennies in the bank. Okay? Because our initial plus the work done is equal to our final. Okay? And we can say the mechanical energy is conserved. It stayed, like, all the money stayed in the bank. There was no change in the total money. Okay? Relationship number 2. Final relationship. Third one is looking at this. Okay? When it reaches the highest point, did it have kinetic energy? Is it moving at the highest point? No. Stops, right? Like at the highest point, stops. Okay? So no kinetic energy. Did it have gravitational potential energy? Was it above ground zero? Yes. Okay? So how much should I put in there? Well, our bank account, our total balance is 5 pennies, so if nothing's in kinetic, so it has to be, all of it has to be in potential.
We shove it over.
Okay? Does that make sense? So you're like,
But what's the
all
amount of
you're
force?
doing is transferring funds from one account to the next. It's still in the bank, it's all conserved, it's just in different accounts.
Money.
Good with that? Okay?
So what about the work stuff?
So from that, you can answer these type of questions. so we understand the types of what we're looking at. So, and you can use these bar charts to give a pretty good, solid argument as to why the correct answer is the right answer. Tell your neighbor what the answer is and why. Okay. Did kinetic energy lose or gain? Lost. Started with 5, ended at 0. Did potential energy gain or lose? Gain. It started with 0 and it gained 5. The loss of kinetic energy is equal to the gain of potential energy in this example.
What is the work effort thing?
There's no work done by non-conservative forces in this example. So, if mechanical energy is conserved, then you know that the change in potential is equal to the change in kinetic. One is gaining, one is losing. But the change will always be equal. Right? If mechanical energy is conserved. Okay? So, let's do the same thing, but now throw in some friction. Okay? So, initial, final, ground 0. Did it have kinetic energy? Yes. It's still moving the same speed as it did initially. Okay? So, our initial conditions are good. Was there any work done by a non-conservative force? Yes. Is friction doing positive or negative work? Negative. How much? I don't know. Let's make something up. Okay, let's say 2. So we're spending 2 pennies. So how much energy did I have left over? I took away 2, so all I can do is have 3 in the bank now. All right. At the highest point, kinetic energy is still 0, so that means I have how many pennies left in my savings account? 3. All right with that? Now, how does that manifest itself in real life? Like, what would this look like? Kids sledding up the embankment with friction compared to original without. What does this tell us? Happens to the kid.
Slows down faster.
Slows down faster, and therefore doesn't what? What can we conclude about? It does not go up as high with friction. Some of that energy was taken away. Right with that? Okay. Just a different way to look at it. And so, based off of this, with friction, tell your neighbor. Kinetic energy lost 5. Potential energy gained 3. Kinetic energy lost more than potential energy gained because some of that was taken away. Good? Okay. Let's look at something a little more complicated. Okay. So you throw a rock at 25 meters a second at 30 degrees off of a 10-meter high cliff. How fast is it going when it hits the ground?
How long?
Okay.
Is really how it is.
So my initial at the top, final at the bottom, ground 0, lowest point I care about, right, make ground 0. Nothing too crazy there. Okay. Initially, do you have kinetic energy? Yeah. How much? I don't know. Let's throw a 3 in there. Okay. Gravitational potential energy. Do you have it initially? Are you above ground zero initially? Yes, you are. Okay. How much? I don't know. I'll give it 5. Okay. So our total mechanical energy is what? Total money in the bank. 8. 1, 2, 3, 4, 5, 6, 7. Okay. How we doing? Okay. So, from the initial to the final, was there any work done by non-conservative forces? Just gravity is acting on it after it leaves your hand before it hits the ground. So, mechanical energy is, so no work is done. Mechanical energy, how much mechanical energy do we have at our final location? Still 8. Okay? At our final location, do we have kinetic energy?
No.
Yes, right as it hits, like if I dropped a bowling ball on your foot, it hurts because it's moving when it hits the ground.
Or it
Okay.
smashes.
And gravitational potential energy, how much do I have? 0. So, all this money is somewhere, not in the savings account, it's got to be in the check. So it's in kinetic. Okay? Good with that? Here's the original equation you're going to be starting with. Okay? That's going to be your best friend, this unit. Okay? Initially, do we have kinetic energy?
Yes.
Yep. Do we have gravitational potential energy?
Yes.
Yes. Do we have any work done by non-conservative forces?
No.
No, that's 0. Do we have kinetic energy at the end?
Yes.
Yes. Do we have potential energy at the end?
Yes.
No. That goes to 0. Okay? Does everybody see, like, we're everybody good with the connection between these two? Okay? Now, what do we do at this point? We substitute in these equations into these energies. Okay? So initially, you have 1/2 mass times speed squared initial. Okay? Plus mass times 9.8 times initial height is equal to final kinetic energy, 1/2 mass times speed squared final. What variables do we not have? Don't have mass. But check this out. See, I have a mass here, a mass there, a mass there.
How heavy is it?
You know what? I don't know.
Maybe it's nothing.
But if the mass cancels out, does that mean the rock is massless?
Nope.
No, what does that mean?
It does not make any sense.
It does cancel, so in real life, what is that, how does that demonstrated?
It doesn't matter.
Doesn't matter. I don't care how massive it is.
How do you cancel out both masses on the other side?
Good question. I am dividing by mass on both sides, so that, I distribute that, but I could do this.
Same people do.
Yeah, you're right with that? So masses cancel out.
Is it like in meters or is it in inches? It's over
It's,
in.
it's separate. It's mass times 9.8.
Okay.
That's how much mechanical
Okay.
energy is in that? Jesus.
Okay, now, so mass cancels out. So I've got 1/2 times 25 meters per second, square that, plus 9.8 meters per second squared times a height of 10 meters is equal to 1/2 mass times speed squared. I have one unknown, I just need to solve for it. Hang on to that. Yeah, hang on to that. I think I know where you're going, hang on to that. Okay, so I get 312, is that right?
This one, I think I'm starting to look copper.
Okay, 312 joules, that's 98 joules is equal to 1/2 speed squared. So 410. So I get A21. And I get
Wait,
That's supposed to be divided by half, right?
Yep, which is the same thing as multiply by 2.
Huh.
No, 28 points, oh yeah, 28.65 meters per second.
We're 28 and 37 squared.
Okay. Now, does this fit in the realm of reality?
Yes.
28 meters a second, it started out at 25 meters per second,
So we're 10.
okay? So yeah, it's gonna be a little faster.
Because we're going into
What thing do we not take into account? What number do we not even deal with, right? Okay, that's true, we didn't do it with air resistance, we're gonna ignore air resistance. What else? What number do we? 30 degrees. Does energy have direction? No. So this was a distractor. It doesn't matter the angle. It does not matter the direction. What? First time in physics, but it doesn't. Because energy doesn't have direction. So
doesn't exist.
what that means is I could shoot this at any angle, and the speed at which it hits the ground is gonna be 28.65 meters a second. Now, when I first heard this, I was like, prove it. And I did some like projectile motion calculations, like, that's true. Oh my goodness, it's crazy. Okay? It doesn't mean which one hits the ground first, but it says when it does hit the ground, they're all gonna go 28 meters a second. Good with that? Okay? Good.
Wait, why is there no work done if you're throwing it?
Great question. So I'm gonna say the initial is right after it leaves my hand. So during the throwing, yes, that would be work, but after it leaves your hand. Okay? All right, so these are the steps we just talked you through. Next example.
Yeah, you gave me 13. Oh my gosh, really?
Okay, so you have a roller coaster. 500 kilogram roller coaster going 1 meter a second at the top of a 20-meter tall hill, then plunges down, races back up the loop. How fast is it going to the top of the 15-meter high loop? The friction does negative 3,000 joules of work. Okay? So, our initial here, final, at the top loop. ground zero. Check this out. Lowest point I care about. Lowest point I care about is right here. I'm gonna make that ground zero. But it goes below that. Yes, it does. But I don't care.
No one cares.
Okay? So it's just the lowest point between the initial and final. Okay? So, initially, do you have kinetic energy? Yes. Okay, initially you do have kinetic energy. How much? Not much. I'll give it a penny. Okay. Initially, do you have gravitational potential energy? Yes. How much? I don't know. I'll give it 4 pennies. Okay. So our total mechanical energy, total money in the bank, 5 pennies. Is there any work done by non-conservative force from the initial to the final? Friction did this much work. Okay, so I'm gonna take a penny away. Okay with that? Hoping friction doesn't do too much work on our roller coaster. Okay? At the final location, do you have kinetic energy? Kind of hope so. It's asking for how fast, so we're assuming there's going to be some speed. Okay? Oops, sorry. Forgot this. Mechanical energy, we're down to 4 pennies. Okay? So kinetic energy, yes, we have it's moving. Gravitational potential energy, do I have gravitational potential energy if I've made ground zero here? No. Okay, so all of my money is now in kinetic. Okay, so this, oops, you're right. That goes to potential energy 0. So check this out. I'm just going to do one color for sake of time. We've got 1/2 mass times the speed squared initial plus mgh initial minus work done by non-conservative force 1/2 mass times the speed squared final. Yes? Now, here's the important part before the bell rings. Your height is what? Distance above ground zero, your height is 5 meters. Okay?
Is it all, you said it's always 5 meters?
No, in this scenario,
Oh,
it's 5 meters
Oh.
above,
yeah.
okay? So you got 500 kilograms times 9.8.
It's on your ship,
Minus 3,000 is equal to 1/2 500 times final speed squared. You have one unknown, and the answer is 9.3 meters a second.
I'm confused how it's 5 meters above ground zero.
Great question. So 5 meters. So we made the highest point we care, the lowest point we care about, ground zero. So the height that we care about above ground zero is just your 20 minus your 15. It's how high this is above where ground zero was. So like here's our ground zero. I want to know how high the roller coaster is above this point.
The highway.